Imagine you could take a perfectly flat, incredibly thin sheet of material and make it act like a powerful lens, a complex hologram, or even an invisibility cloak. That's not science fiction anymore, that's the world of metasurfaces. Think of them as smart surfaces. They are ultra-thin, two-dimensional arrangements of tiny, nano-sized antennas. These aren't antennas for your radio, though. These are antennas for light. By carefully designing their shape, size, and spacing, we can tell light exactly what to do when it hits the surface. It's like being a traffic cop for photons, directing them to bend, focus, or scatter in ways that were once impossible with conventional optics. So, how do they work? It's all about manipulating the phase of light. When a light wave passes through a normal lens, the curved glass slows it down more in the thick center than at the thin edges, causing the light to bend and focus. Metasurfaces achieve the same effect, but without the bulk. Each tiny nano antenna on the surface imparts a specific, calculated delay to the light wave that hits it. By arranging these antennas in a precise pattern, we can sculpt the wavefront of the light into any shape we desire. We can create a sharp focus, split a beam into multiple beams, or even twist light into a corkscrew shape. It's an incredibly powerful way to control light on a microscopic scale. This level of control opens up a universe of possibilities that go far beyond what our current technology can do. Your smartphone camera, for instance, uses a stack of several curved plastic or glass lenses to capture a clear image. This lens stack is what creates the camera bump on the back of your phone. Metasurfaces could replace that entire bulky stack with a single, paper-thin sheet. This would not only make our devices slimmer and lighter, but also potentially more powerful, allowing for new kinds of imaging and sensing that we can't even dream of today. It's a fundamental shift in how we think about and engineer optical systems. Consider the simple act of seeing. Light bounces off objects all around us and enters our eyes, where the lens focuses it onto our retina. Metasurfaces are, in a way, a superpowered, engineered version of this natural process. But instead of just focusing light, they can sort it by color, polarization, or direction. They can create images that appear to float in midair, like the holograms we see in movies. They can steer laser beams without any moving parts, or absorb specific colors of light to make an object appear different. This technology is about taking our relationship with light from passive observation to active, precise manipulation. It's about building the future, one nanostructure at a time. For a long time, the go-to materials for building these light-bending nanoantennas were noble metals like gold and silver. Why? Because of a cool phenomenon called plasmonics. When light hits these metals, it can cause the electrons at the surface to slosh back and forth, creating collective waves of electrons called surface plasmons. These plasmons are fantastic at confining light to incredibly small, sub-wavelength spaces, which is exactly what you need to make tiny antennas work effectively. Gold and silver became the stars of the show in the early days of metamaterials research, allowing scientists to demonstrate all sorts of amazing optical tricks and prove that the basic concepts were sound. However, gold and silver aren't perfect. In fact, they have some pretty major drawbacks that hold back the technology. One of the biggest problems is loss. While the electrons in gold and silver are great at oscillating, they also tend to bump into things and lose energy, which is then converted into heat. This means that a significant portion of the light that interacts with a gold or silver metasurface gets absorbed and wasted instead of being usefully redirected. This is a huge issue for devices like lenses, where you want as much light as possible to pass through and form a bright, clear image. It's like trying to fill a bucket that has a big hole in it. Another issue is that gold and silver are, well, gold and silver. They are soft, they don't play nicely with the standard manufacturing processes used to make computer chips, like CMOS fabrication, and they are not very durable. Gold can't handle high temperatures, which is a problem if you want to build devices that can withstand powerful lasers or operate in harsh environments. Imagine trying to make a lens for a high-powered industrial laser cutter out of a material that melts easily. It just wouldn't work. We needed materials that were tougher, more efficient, and more compatible with the way we already build our modern electronics. Finally, the optical properties of gold and silver are fixed. You can't change them on the fly. Once you've fabricated a metasurface out of gold, its function is set in stone forever. This is a major limitation for creating dynamic devices, lenses that can change their focus, or holograms that can switch between different images. For technology to truly advance, We need tunability. We need materials that can respond to an external signal, like an electric voltage, to change how they interact with light. The limitations of noble metals made it clear that to unlock the full potential of metasurfaces, the scientific community had to look for a new class of materials. So, scientists went on a hunt for better materials, and they found some amazing candidates in some unexpected places. Enter the new heroes of plasmonics: Transition Metal Nitrides and Transparent Conductive Oxides. These might sound complicated, but they are game changers. One of the stars is titanium nitride, or TIN. You might already know it as the hard, gold-colored coating on drill bits that makes them last longer. It turns out that this super tough material also has fantastic optical properties. It behaves a lot like gold in the visible spectrum, supporting plasmon resonances, but it's much less lossy. Less light gets wasted as heat, meaning more light can be used for the device's main purpose. Titanium nitride and its cousin, zirconium nitride, are also incredibly robust. They are ceramics, which means they are extremely hard and have very high melting points. We're talking thousands of degrees Celsius. This makes them perfect for applications that gold and silver could never handle, like thermal emitters or devices that need to operate under intense laser light. Plus, they are fully compatible with the CMOS manufacturing processes used to make the computer chips in your phone and laptop. This is a huge deal. It means we can potentially manufacture these advanced optical components using the same factories and techniques we already have, making them much cheaper and easier to produce on a massive scale. On the other side of the spectrum, we have transparent conductive oxides, or TCOs. A great example is indium tin oxide, or ITO, which is the see-through material used in your smartphone's touchscreen that allows it to detect your finger. TCOs are special because their optical properties can be tuned. By applying a small electrical voltage, you can change the number of free electrons in the material. This, in turn, changes how the material interacts with light, particularly in the infrared part of the spectrum. It allows us to switch the material from being reflective to being transparent, or to actively change the phase delay it imparts on a light wave. This is the key to making reconfigurable metasurfaces. The combination of these new materials is what's truly unlocking the future. We can now choose the right material for the job. For a static, highly efficient lens that works with visible light, we might use titanium nitride. For a dynamic device that needs to change its properties in real time, like a tunable filter or a beam steering device for LiDAR systems in self-driving cars, we would turn to transparent conductive oxides. These materials give us a full toolbox to design metasurfaces that are not only thin and efficient, but also durable, manufacturable, and dynamically tunable. They are the building blocks that will take metasurfaces out of the research lab and put them into our everyday lives. So what does all this mean for you? The practical applications are breathtaking. Let's start with those ultra-thin lenses. Imagine replacing the heavy glass in virtual and augmented reality headsets with a single, flat metasurface lens. The headsets would become as lightweight and comfortable as a regular pair of eyeglasses. Or think about high-resolution holograms. With tunable metasurfaces, we could create truly three-dimensional displays that can change their image in real time, moving us one step closer to the holographic communication we see in movies. These aren't just incremental improvements, they are revolutionary changes to how we interact with digital information. Metasurfaces also give us unprecedented control over the direction and shape of light. This is crucial for technologies like LiDAR, which self-driving cars use to see the world around them. Current LiDAR systems use bulky spinning mirrors to steer a laser beam. A metasurface could do the same job with no moving parts, making the system smaller, more robust, and much faster. In communications, we could use metasurfaces to precisely aim data-carrying light beams, creating ultra-high-speed wireless networks that are more secure and efficient than Wi-Fi. It's about making light do our bidding with incredible precision. But the control goes even further, into the realms of heat and energy. All objects that have a temperature, including our own bodies, emit thermal radiation, which is a form of infrared light. Metasurfaces can be designed to control this emission. We could create surfaces that radiate heat very efficiently in specific directions, leading to better cooling for electronics. Or we could do the opposite, create coatings that prevent heat from escaping, leading to better insulation for buildings or even thermal camouflage that could hide an object's heat signature from infrared cameras. This is called controlling absorption and emission, and it opens up a whole new frontier in energy management. Ultimately, metasurfaces represent a paradigm shift. For centuries, our ability to control light has been limited by the materials nature gave us, and the shapes we could grind them into. Now, we are designing materials from the atom up to command light with near-perfect control. This will impact everything. It will lead to medical imaging devices that can see diseases earlier, solar panels that capture more energy from the sun, and computing that uses light instead of electrons for faster, more efficient processing. The future will be built on our ability to engineer light, and metasurfaces are the key that will unlock that future. Consider this. The screen you are reading this on is a flat surface that controls light to create an image. Metasurfaces are the next, much more powerful, step in that evolution.